In this video, I'm going to discuss modeling a system of objects in one dimension. So we have two objects here. We have a person and an elevator. And what I've tried to show here are two instances of time. So from the looks of things, if you start here on the left-hand side and a moment later you're here in this right picture, you can see that the elevator is traveling downward. So that's what I'm trying to depict here. This is the same elevator, I'm just showing it side by side, and it's starting out here at some position that's above this other one. And it's the same elevator, I'm just showing it side by side. So in these two snapshots here, we have two objects. We have an elevator and we have the person inside of the elevator. Now, if the elevator is initially traveling downward with some velocity, we'll call this v1, and a moment later that velocity has changed and it's now a smaller vector, and we call this v2, well, what's happening here? Clearly, the vectors have shortened from the first instance of time to the second one. And so if we're looking at these two vectors, and we can just pull them out here to kind of analyze them individually, we have v1, and then v2 is this shorter vector. Well, what is delta v in this case? So the change in velocity. Well, we're starting with a longer velocity vector and we're ending up with a smaller one. So delta v would be v2 minus v1. And just looking at these, this is going to be a smaller number, v2, minus a larger number, v1. So delta v is going to be, if we have the negative of this vector, that means we flip it to add them. So we have this v2 vector that's going down like so. This is v2. And negative of v1 is now going to flip v1. So we have negative v1 now is pointing upward, and now we can just add them. So this is then delta v is equal to v2 plus the negative of v1. This is the same. And if we look at these vectors then, and we just kind of do a geometric vector analysis without any numbers, this negative v1, now delta v is going to be the sum of these two. So it's going to be a small vector pointing upwards. So this will be delta v. Delta v is the combination of v2, which points down, and negative v1, which points up. So the ending vector then, when I combine these two together, is going to be a smaller vector pointing up. I'm going to subtract this downward vector from this upward vector, and I have this little upward vector that's left over. And delta v over delta t is known as acceleration. So it's accelerating upwards, opposite of the direction of motion. Remember, the elevator's going down, but the acceleration is pointing up. It's the same as delta v. So what's that going to feel like if you're on an elevator? And I encourage you to just stop and pause for a second, close your eyes, and think about if you've ever been on an elevator that's accelerating upwards, or if you're on an elevator that's going downwards, but then is starting to approach the floor that you're trying to reach. Well, if you're going downward and you're starting to approach the floor where the elevator has to stop, so the elevator is going to have to slow down as you're going downward. And your body is going to continue wanting to move downward at that same speed. But the floor of the elevator is going to push up on you. What that's going to feel like as the floor is pressing up on you is you're actually going to feel heavier than you actually are standing on Earth. And it's not just some trick that your mind's playing on you. If you put scale that we can measure our weight. If you would put a scale in the elevator and actually stand on top of it, and then do this experiment where you're going downward and then you're measuring your weight as the elevator starts to slow down, you would notice that you actually weigh more. Your apparent weight would be larger than your regular weight that you would take if you're just standing still. So that's kind of cool. And if you're moving upward, something different happens. So say instead that, now you're on some elevator and the elevator is moving upwards at a constant speed. So now you're just standing in the elevator and you're moving upward and the elevator has some constant speed. Well, what's going to happen? So you're going to start to slow down in the next instance of time. If you're reaching your floor and you're going upward, you're going to start to slow down, but your body is going to want to continue at the same velocity v. But the floor is dropping away from you, is actually what's happening while your body is moving upward, and your weight will actually do the opposite. If you have a scale while you're going upward in an elevator and then it slows down as it's approaching its floor, you'll notice that your apparent weight is actually less than your real weight because the acceleration now is moving in the other direction. It's accelerating in the other direction, meaning it's slowing down, but your velocity is going upward. So you're going to feel lighter. It's as if your body is going to want to raise off of the scale a little bit. And it's the same feeling that you get if you go over a large hump or a large bump in your car and your body raises off the seat, but the car goes downwards. So you start to feel a sensation where, or if you've ever gone over a sharp crest in a roller coaster, you feel a little bit less, you feel almost weightless for a second. And that's what you're feeling. You're feeling your apparent weight change between you and what you're touching. Let's go back now to the case of the person in the elevator that's moving downward, and then the elevator has to slow down as it's reaching the floor. We would actually have to make two separate free body diagrams. Not for these two different instances, but I'm saying at one instance in time, you would take any moment here, and you'd say, okay, now we're going to only look at this one instance in time, and we're going to create a free body diagram for the person and for the elevator. So I just want to make that clear. I'm not making two separate free body diagrams for these two moments in time. I'm choosing a moment in time, and I'm saying, hey, now we make the free body diagrams, and let's look at what's happening to the motion. So what would the free body diagram be for the elevator? So I can represent the elevator as a dot, and you would have a tension force from the cables that are holding the elevator upward. So you have this tension force upward. You would have, of course, the mass of the elevator times gravity, which would be equal to the weight force pulling it downward. And then there would be another force that the elevator would feel. And that is if you have to look at this now from the elevator's perspective, and the elevator is going to feel this person that's also pressing downwards on it. And you can call that, generally just F of the person on the elevator. And it's actually a normal force that is pushing downward. So I'm going to call it negative N. It's pushing downward. It would be, at this point right here, what the elevator is feeling from this person's 2 feet pressing downward on it. So it would be this normal force right here, and it's pointing in the downward direction. Okay, so what about from the person's perspective? So this is the elevator. And now we need to make a free body diagram for the person because it's two separate objects. Yes, they're in the same system, but to actually analyze the individual forces, we have to consider both objects independently. So first I've looked at the elevator, and now I'm going to look at the person. And once again, we have just a dot to represent the person. And we're going to have this mass of the person times G, Now, this is not going to be the same as the mass of the elevator times g. Obviously, the elevator is going to weigh a lot more than a person. So if I call this the weight of the elevator, then this I would call the weight of the person. I don't want to use W and just keep it by itself because I have to differentiate between these. These are going to have a different mass. The elevator is going to have much more mass than the person, who's going to have less mass. So this vector is also going to be smaller than the vector on the elevator. So, okay, so you have the mass of the person times gravity, that's the weight force. And then you're going to have this upward normal force, and it's going to be the force of the elevator on the person. So it's going to be like this, and this is going to be the force of the elevator on the person. And this is going to be equal and opposite to the normal force that's in the negative direction. Now this is going to be a positive normal force. So this is equal to positive of the normal force. And one thing we can say about both the elevator and the person, they're the same system. So, you know, as I'm looking at this as a system, there are these different forces that are going on. But what can I say would be shared between the person and the elevator? They're going to be sharing the same velocity as long as they're touching. They're sharing the same velocity. So they're also going to be sharing the same acceleration. They're not going to accelerate independently of one another because they're connected. They're touching one another. So the acceleration on the elevator, remember we found that here, it's going to be the same for the elevator as it will be for the person. Both of these will have an acceleration pointing upward, and they're going to be the same because they're connected. The person and the elevator are touching. So when you look at these two now, we have these separate free body diagrams. And with these free body diagrams, we can create some equations from Newton's second law. We have all these forces here, and what does Newton's second law say? Well, Newton's second law says that the sum of the forces is equal to mass times acceleration. And that's going to be the case for both of these objects. The sum of the forces equals the mass times the acceleration. So now I can start writing, hey, what are the sum of the forces? What is the mass and what's the acceleration? So, okay, first I have a positive tension force, and then I have a negative m sub e times gravity, so that's the weight force. And then I have this negative force of the person on the elevator. And what is that equal to? Well, that is equal to the mass of the elevator times acceleration. So all I've done is I've literally done what Newton's second law tells me to do. I add up all the forces and I just look at their directions. So the T is pointing upwards, it's positive. The weight force is pointing downwards, so it's negative. The force of the person on the elevator is pointing downwards, so it's negative. And these are equal to the mass of the object times the acceleration of the object. I don't give the acceleration a subscript because it's the same for the elevator as it is for the person. So it's the shared acceleration of both of these. Now I'm going to do the same thing for the person. So I sum up all the forces. I have a positive force of the elevator on the person, and I have a negative mass of the person times gravity, and this is equal to the mass of the person times acceleration. So again, I've just rewritten what Newton's second law tells me to write. And from this point, now we have the general equations, and we can look at these bottom two equations, and you'll notice a few things. So first we have this force of the person on the elevator and this force of the elevator on the person. We know the magnitudes of those are the same. So we could equate those two values together. You could solve for the force of the person on the elevator, and you could solve for the force of the elevator on the person, and then you could compare these two directly. You could combine these two equations because they'd have something that's the same. We know the magnitude of these two values are the same. You could also look at other values. You could look at, for example, you could solve for the tension force and relate the tension force to these other values here. Once we have these two equations, we can tell that there's something that's shared between two of them. And why is that the case? Well, because the acceleration is shared, and because we have a Newton's third law pair with the force of the elevator on the person and the force of the person on the elevator. So there are commonalities between these two separate objects. Why? Because they're accelerating together and they share a Newton's third law pair. Typically, the hardest point is to get to where we've arrived at. We have these two equations. These equations have come directly from the free body diagrams, and usually once you get to this point, then you can plug in simple values that will be given to you in the problem statement, like masses, different forces, maybe a tension force, the mass of the person or the elevator, what have you. You'll usually be given values, and at this point you can solve for other quantities as needed. So this is just one strategy to solve for a one-dimensional system and how to model it appropriately.